questions? I would have been lost there. Oh, okay. Yeah. Thank you. Question?
I'm confused.
You're confused. Good. All right. What's the? Because there's probably others too.
So if you have less protein in the blood, it's gonna, I thought it would decrease filtration because it's like not a bigger difference in concentration gradients. Like it wouldn't want to move down as much because there's less.
Let's go back here and look at it. Maybe the illustration here will help. Okay. What we're talking about is this variable right here. Okay. So this is the biggest variable holding us back from filtration. Okay. So it's 28, and if we run the numbers, we get something like 17, right? If that 28 gets smaller, right, because we have less protein in the blood, right, that will mean that our net filtration pressure will be bigger because we're subtracting this number. Okay. All right, what about the next one? Kidney stone in the collecting duct, or anywhere further on down the line. Okay? It could be in the renal pelvis, the ureter. What would this do? Would that affect filtration?
Would it increase the pressure in the Bowman space?
Yes, it would increase the pressure in the Bowman space. Okay? So you can think of this as, in very broad terms, this is a blockage preventing fluid from passing through the tubular, the tubule, right? So this would elevate the pressure in Bowman space. Okay? That fluid is supposed to pass freely out of Bowman space, down the proximal tubule, and along through the rest of the nephron. If there's something obstructing, making the flow of fluid difficult, that's a lot of resistance, right? And that's going to elevate your Bowman space pressure. Okay. So if we elevate Bowman space pressure, what happens to GFR? Yeah, it's going to decrease. Anybody get them all right so far? Nobody? Good. That means you're learning stuff. Okay. All right, what else do we have here? All right, and glomerular, if you can't say glomerular, try glomerular, I can't say it. Glomerulonephritis. Okay. Glomerulonephritis is an inflammation and eventually breakdown of that filtration membrane. Okay, so what happens there? Anybody have an idea if we break down our filtration membrane, how that would affect GFR? Surface area might be affected, but what would be, what's another way that we can affect that if we're breaking down that membrane? You're going to start letting things through that shouldn't get through there, right? It's going to become more porous. Okay, I would say the surface area is probably not going to be terribly affected. You'll still have the same length of capillaries there for exchange, but the porosity would change, right? They become more porous as they break down. So if we change the permeability, make it more permeable, what's going to happen to filtration? More permeability means what happens? More filtration. Okay. So why does, let's make sure we're clear on that. Why does increasing permeability mean more filtration? More stuff can get through that filter, right? We're making the holes bigger in the filter, so fluid passes through more easily. Okay? All right, so this is actually a double whammy. What else would happen if you started making that barrier more permeable. What might pass through that ordinarily doesn't? Proteins, okay? And if we suddenly have proteins in Bowman's space, what happens? Yeah, we're going to change osmotic pressure. Okay, so let's take a quick look at that here, right? So if we suddenly have an increase in permeability, we're going to start collecting proteins out in Bowman's space where there usually are none. Okay, so what value goes up?
Osmotic pressure, building factor.
Yeah, osmotic pressure of Bowman's space. Okay, so usually there's not much osmotic pull, not osmotic pressure, because there's no proteins here. But if we start adding proteins, we're going to enhance this, right? And so what is that going to do to filtration? Increase filtration, right? It works in the direction of filtration. So we increase osmotic pressure of Bowman's space by letting proteins in, right? And that increases GFR as well. So glomerulonephritis is a bad thing, okay? Because we're going to start losing lots and lots of fluid. Okay? Remember from your reading how much fluid we filter in a day? 125 milliliters per minute is about 180 liters a day. Okay, that's a lot of fluid, right? And if we make this worse, we're going to have a hard time pulling that back into the body. Okay, so GFR is an important thing. And as we'll talk about a little bit later, we have ways of controlling GFR to keep it in check when things happen. Okay, when certain pathologies get too bad, though, like this glomerulonephritis, there's not much we can do. Okay, so why is GFR so important? Let me see if I can. Let's see if the audio. You don't need it. This is from something called television. But you can see this is a great analogy for GFR. Right? We make this fluid with our solutes in it, and it starts flowing through the nephron. So reabsorption relies on transporters, right? Like we see enough here. Okay, and transporters pull things out of the fluid at a predictable rate, something we can measure. But when that fluid starts to move very, very rapidly, if we have a high GFR, we've got a lot of fluid running through the tubule rapidly, what happens to reabsorption compared to normal? Will we reabsorb more than usual or less than usual? Less than usual. In other words, more of these solutes pass by the transporters without being reabsorbed. Okay. So sodium is a great example of this, right? So sodium, we reabsorb something like 97% of sodium, 95% of sodium. But if this GFR becomes very high, we're not going to get quite the same number. Maybe we only get 90% of it and we excrete more. Okay? So reabsorption of chocolates, solutes, reabsorption will, if GFR is high, we'll have a low reabsorption, and the opposite, or the result of this, I guess, is that the excretion of that solute will be higher than normal. Okay? The opposite could be a problem too, right? What if it goes too slow? And we're supposed to reabsorb 95% of the sodium. What if that GFR slows down and it's just crawling past, barely moving past those transporters? What are they gonna do? They're gonna pull it all back, right? And excrete nothing. So the normal processes of secretion and reabsorption, reabsorption is probably the most important of the two, but they rely on a normal GFR. Okay, so as much as possible, the body likes to keep GFR normal, right? And that means we keep plasma protein concentrations constant, we keep hydrostatic pressure in our circulatory system constant, so that we have a constant rate of filtration. Okay. But as you know, we've talked about examples where blood pressure changes, right? So you can imagine that there's going to be cases where blood pressure is a little too high, a little too low, and we have to make adjustments to GFR. Okay? So we've got a really cool mechanism of being able to adjust GFR using these two arterioles we have. It's an example of auto-regulation. Okay? Meaning this is not resulting from hormones, it's not resulting from nervous system signals. This is every nephron for itself. Okay? There's sometimes they might all act in accordance. Right? So if you've got low blood pressure, all of the nephrons will probably respond the same way. But if you've got a local blockage that doesn't affect both kidneys or even all of one kidney, some of those nephrons will respond while others don't. Okay, so think of this as autoregulation, just like we have autoregulation of other blood vessels in the body. Okay? So let's take a look at on the left-hand side. Afferent arteriole, AA. All right, afferent arteriole. When it constricts, what is the thing that's affected in that glomerular capillary downstream? You can see it listed up there. Yeah, we're letting less blood into that glomerulus, and so that glomerulus now has a lower hydrostatic pressure. Okay, so the hydrostatic pressure of the glomerular capillary is lower as a result of that afferent arterial constriction. Okay, so this is squeezing off the blood supply to that particular glomerular capillary. Okay? And you squeeze off the blood supply, its pressure is going to drop. And of course, with that, we lower NFP, and then that lowers GFR. You with me? Okay. The opposite's true. The opposite here, that on the left, we dilate the afferent arteriole, we let more blood in to that glomerular capillary, and the pressure in that glomerular capillary goes up. We raise the glomerular pressure, we're going to increase NFP, and we increase GFR. So you'll notice in all these diagrams here, that glomerular capillary pressure and GFR always are going to move in the same direction, right? Because the pressure in the glomerulus is a determinant of NFP, and NFP is a determinant of GFR. Okay. All right. So what we're doing here, I know we've struggled in the past with the sort of upstream, downstream constriction, resistance, pressure, flow thing. We are adjusting the flow of blood into the glomerular capillary. Right? And when we adjust the flow into that capillary, we either let more fluid, more blood in, and that raises the pressure, or we let less blood in, and that lowers the pressure in that capillary behind the afferent arteriole. Okay. Now, the efferent arteriole is the one downstream of our capillary. Okay. And if we constrict the efferent arteriole, we are elevating resistance upstream that is in the direction of that arteriole. Okay, so blood's flowing towards that arteriole. Right? And we're going to increase resistance everywhere in front of that arteriole, right? That is in that direction. That's an arrow. Not a good one, hang on. Okay, we're gonna increase blood pressure upstream of that constriction. Okay. So if we increase resistance, we increase blood pressure in the glomerular capillary. Okay, and that's going to elevate GFR. Okay, the opposite, right? On the bottom, if we dilate that efferent arteriole, we're letting blood easily pass through. We're lowering resistance, and blood can easily get out. So, what do we do when we have high blood pressure and we're in danger of having a GFR that's too high? What are we going to do? GFR is becoming too high. What are we going to do?
Constrict the afferent arteriole or dilate the efferent.
Constrict the afferent arteriole or dilate the efferent. Okay. So if blood pressure is too high, the response of these arterioles is to constrict, like the afferent arteriole, or to dilate, in the case of the efferent arteriole. And both of these will work together to lower GFR so that we can get it back to where it needs to be. Okay? So we don't regulate GFR directly, but those arterioles are responsive to blood pressure. Okay? So they will respond to high blood pressure in opposite ways. The afferent arteriole will constrict, the efferent will dilate. Okay? Okay, so let's say you have renal arterial stenosis. Good for you. You've got a narrowing of the blood vessel going to one of your kidneys. So for those nephrons in this region, what's going to happen as a result? So you certainly want to confer with somebody close by. I'm amazed. Okay. Wait a minute. Okay. So we have stenosis, narrowing of the blood supply to the kidney. So what's going to happen to blood flow generally to our nephrons? It's going to be decreased. Okay. And what's the effect of that decreased blood flow? Decreased pressure within our glomerular capillaries. Okay. So how do the afferent arterioles respond to that lower pressure? They dilate. They dilate. Okay. So in response to the low pressure that will threaten GFR, right? GFR could get too low, right? If our pressure is too low. Those afferent arterioles respond to the low pressure by dilating. Okay, and what happens then to our glomerular hydrostatic pressure when those afferent arterioles dilate? It'll go back up, right? So you can see how this is auto-regulation. We're going to have a low glomerular pressure, right? And the response elevates it, right? So we're back to where we need to, right? The homeostatic response. Okay. What's the other thing we could do with the efferent arteriole? Constrict, right? Provide resistance to that blood flow, right? And the pressure upstream of that constriction of the efferent arteriole would raise glomerular pressure as well. Okay? So they work together, but they work in opposite directions. Okay. So with the time that's left, let's talk about reabsorption. Everybody cheers. And reabsorption is an important process, right? And just the numbers from filtration should convince you of how important reabsorption is, okay? So we filter about 180 liters of water per day out of kidneys. How much water do we have in our blood? Anybody know? Or how much blood volume do we have? Like 4 or 5 liters. Okay, we've got 5 liters of blood. Okay. We are filtering 180 liters per day. Okay, so many, many times our own blood volume is lost to the kidneys. Okay, and we don't pee that much, fortunately. Okay? There's nothing left of us. But what we do is we pull it back. Okay, sodium, glucose, urea. These are all things that we really produce lots of. 630 grams of sodium. Okay, it's over a pound. All right, so how much we actually excrete is far less. Okay, so we excrete about almost 2 liters of urine a day. Okay, or almost 2 liters of water in a day's time. Okay, depending on how much you're drinking. Okay, we actually lose just a little bit of sodium, right? 3 grams out of 630. Okay, very small percentage. Glucose, we pull all of it back, right? Unless we've got a problem, right? And urea, which is a waste product, so we get rid of some of it, but not all of it. Okay. But we get rid of enough of it. So how do we explain this? Well, it's reabsorption, right? Reabsorption is the process by which we can reconcile how much is filtered and how much we actually excrete. Okay. So what is reabsorption? All right, so if you take a look here at the tubule, you can see a little peritubular capillaries wrapped around it on the left. If we look at just a little section of that, we can see we have epithelial cells, okay, making up the tubule wall. What would you say about these? Are they squamous? Or, whatever. They're not cuboidal. They're cuboidal, columnar, somewhere in there. Yeah. It depends on the region of the nephron, but they're generally considered cuboidal. There's some places where they're more columnar. Okay. So they're kind of thick, right? And that's important because we're making a barrier, right? When we talked about alveoli, we talked about endothelial cells, where we want lots of things to move quickly. We use squamous cells. When we want to make a barrier, a selective barrier, we're going to use something a bit thicker, like these cuboidal or columnar cells. Okay? And there are tight junctions. Tight junctions are those little brown things here that help to hold the cells together. Okay? So all the way around that cell, making connections to the cells, to the right, to the left, in front of, behind, we've got a sort of a belt of tight junctions that go all the way around that helps define a barrier. And that barrier is between what's in the interstitial fluid of the lumen, right? And what's in the interstitial fluid on the other side of the cells, by the blood. Okay, so we've got different ways of transporting. Two major ways we transport across this epithelial boundary. Okay, one is through those tight junctions, or through the spaces rather between tight junctions, and this is called paracellular transport. Okay, so mostly what moves through here is water. Okay, and occasionally some ions get dragged along with that. Okay, this is paracellular transport. And it relies on tight junctions that are not super tight. Okay, called tight junctions, but depending on how many of them are, we can have lots of movement through this space or practically no movement through this space. So here, we've got some movement. So we might call these leaky tight junctions, or not so tight junctions. Okay. They hold the cells together, but they're not preventing water to move through. Okay. The other type of movement is through transporters. Okay, this is transcellular transport. So a substance will go through the cell. So glucose, for example, will go from the lumen of the tubule, right? It was filtered, so it's going to be in that tubular lumen. And it'll get transported into the cell, and then it'll get transported out of the cell on the opposite side. And then it will have made its way through, right? And the blood's on the other, it can get swept away in the peritubular capillaries. So there's two different paths that substances can take, okay? There are parts of the tubule that are completely impervious to water transport. And the reason for that is that they have tight junctions, okay? Or in other words, a very high density of these junctions that prevent fluid from moving through. And the only way things can get through is with transcellular transport.
You said for the paracellular transport, water isn't allowed to pass through?
For paracellular transport, if we have lots and lots of tight junctions, here called tight junctions, water is not going to be able to pass through, okay? But if they're more loosely, have a looser density, then we can get water passing through. Okay, so it depends upon the density of those tight junctions, how many there are on a given cell. Okay, so what we'll learn about eventually is that certain regions, like the proximal tubule, are much leakier and allow lots of reabsorption through this paracellular path. Okay, but then we get down to the collecting duct, right? And we might not have any water permeability through this paracellular path at all. Okay. The other way that water can move is through aquaporins. Okay. We'll talk about that when the time comes, but that would be classified as a transcellular pathway, right? Okay. So we can move things very selectively if we take advantage of all these transporters that we have. Okay, so let's take an example. We'll take glucose. Glucose, and this brings us back to the idea of epithelial transport that we've touched on briefly in the past. We'll see more of it. Glucose is something our bodies need, right? It makes no sense to waste glucose because it's a fuel source. Okay, so how do we reclaim all of that glucose that we have filtered? We filter about 1/5 of the plasma, 20% of the plasma. So 20% of the glucose goes with that 20% of the water. Okay? So 20% of the blood glucose by molecules is going to end up in the filtrate, in the tubular fluid. Okay? And so if the blood has 100 milligrams per deciliter of glucose, we'll have the same thing in the lumen of the tubule. Okay? It's 1/5 of the rate. So how do we get it out? Well, you tell me what's going to happen here. What's the prime mover in this little system? Remember how we looked at these things in the past? What's the first thing you look to? It starts with primary. Primary active transporter. What's the primary active transporter doing? What is the primary active transporter doing? We're making a gradient of sodium. Okay, so sodium becomes high outside, and very little inside. Okay. So we've got lots of sodium outside the cell, and we've got very little inside. Okay, so if we drive down sodium inside, what can we say about this secondary transporter on the left? We drive down the sodium inside, what's going to happen to our secondary transporter? Yeah, it's gonna want to pull that sodium inside, and along with it, it'll grab a glucose. Okay. So what happens glucose when we do this? Goes down in the lumen, it goes up where? Inside the cell. So glucose goes high inside the cell. Okay? And then what do we have on the other side here? Glucose transporter. What are those arrows telling you? It could go either way, right? And what's going to determine which way it goes? Concentration. Okay? So you might remember we called this side of the cell the apical side. All right, what do we call the other side? The basolateral side. Okay, in particular, we're talking about the membranes. Okay, so the way that this is set up is that, and we've got, by the way, we've got tight junctions joining one cell to the next here, and also forming a kind of a barrier. Okay, so these sodium glucose transporters, SGLT, can float around the membrane, right? But it can't get past those tight junctions. Okay? So it's always going to stay on its side. It's always going to stay on the apical side. Okay? And the same with our active transporter and our facilitated diffusion glucose transporter. It can move around in the membrane, right? But those tight junctions keep those domains of the cell membrane separate. Okay? So that we keep things in the right place, right? So this lumen over here and the interstitial fluid over here are two separate compartments in a way. Okay? And things have a lot of trouble sneaking by the cells because of the tight junctions. Okay? We're able to move substances like glucose across the boundary of cells. Okay? And then once we accumulate glucose down here, right, it's going to flow into the blood. Okay? So we deplete glucose from the lumen, and we push it into the blood. Okay? And we need active transport to do this because it requires energy. Okay? And ATP is not directly coupled to glucose transport, but you can see here through the secondary transporter, we're going to be using that ATP energy to move glucose. Okay? All right, so 4 minutes left. Let's get an easy point. So of these spaces, and understanding how glucose is transported, where would you expect to find the highest concentration of glucose in this system? Is it in the lumen? Is it in the cells? Is it in the interstitial fluid?